So these are the contents of my presentation: the introduction, experimental work. I will be going through the characterization, then the results in discussion, and the problems that we have been facing, and the conclusion and the references. So this work was, this total list of the presentation I'm going to present is taken from this, the reported work that was published in SES Catalysis. So let's begin with the introduction. So normally, because of the human activities, there is huge amount of about 37 gigatons of carbon dioxide is being produced in our environment. So it has resulted in many global problems like increasing temperature, like the rising sea level, melting of the polar ices, etc. So and every day there if the process continues and the carbon dioxide goes on increasing in our environment in the stratosphere, the temperature can rise up to 6 degrees to the till the end of this century. So we have to take the initiative steps to reduce the CO2 reduction. So the scientists have developed many methods. Scientists have developed many alternatives to reduce the CO2 emission, as well as developed some tools or methods, as well as the materials to convert this CO2 into some useful materials. So using sunlight, which is an inexhaustible source of energy, if we can capture 10% of the solar energy falling on Earth, that's 0.3% of the land surface, it will be sufficient for meeting our energy demands up to 2050. So among those methods, the one that I'm reporting here, presenting here, was the development of the ternary cadmium sulfide / BCN composite nanomaterial photocatalyst by the photo deposition method to convert CO2 into hydrocarbons as a methanol or some other useful products like hydrogen or other green fuels. The photocatalytic conversion of carbon dioxide into valuable products can provide energy in a sustainable way with the leveling of the concentration of CO2 in our environment. Here you can see this is the picture of our composite material, means where there it is deposited photo deposition of this cadmium sulfide on the BCN semiconductor nanomaterial. And this is the process of using the solar light, sunlight, and converting CO2 into CO and other useful products with the help of the positive holes and the negative the charge carriers. So actually, the photocatalyst, the working mechanism is if we may briefly describe, is a substance that uses light energy to facilitate a chemical reaction. There are vast varieties of the photocatalysts which are using the solar energy, the solar light into different ways. Like it is mimicking the natural photosynthesis used by the plant system and generating some other materials. And also there is another way, like converting this solar light into some kind of the charge species, which ultimately convert the carbon dioxide into useful products such as the carbon monoxide and farmers, etc. So we will be focusing on this. So this is the generalized mechanism for the reduction of the CO2 to some other useful products. So means what happens, the light falls on the photocatalyst, and it generates the positive holes and the negative electrons, which later on generate the radical oxygen and hydroxides and other products which interact with the carbon dioxide and convert it into the respective products. Though this is not exactly what we will be representing here, this is generalized model. Okay, though we have discussed so far that reduction of carbon dioxide using the photocatalyst, though it's not that easy as we are discussing, because carbon dioxide is very stable molecule. It has the high reduction potential. So it's not that easy. Here we have the different reduction potentials of the carbon dioxide when we are converting it into the different products. So it is a good challenge for the scientists to utilize and decrease the reduction potential or the activation energy of CO2 to make it means less we can say the expensive. So we have deposited we have deposited with the help of the solar light the cadmium sulfide because of it has this reasonable band gap that is extending from 2 point something to minus 1 point. Okay. So the experimental work that includes for the synthesis of the photocatalyst, it is divided into two parts. The part A involves the synthesis of the precursor BCN material, or we can say the semiconductor material. So the step one involves the mechanical grinding as a kind of top-down approach. It means so the precursor BCN semiconductor was synthesized by mechanical grinding with agar mortar by mixing with boric acid, urea, and starch with the wet ratio of 1:2:5 respectively. Later on, it was treated with the ammonia at high temperature around 1250 degrees centigrade for 5 hours. The final product was washed with hot acetal to remove unreacted product impurities. In the step two, this synthesized material was deposited with the cadmium selenide by photo deposition method. So the procedure involves the 100 gram of the product BCN was treated with the mixture of S sulfur 8, 9 milligram, and cadmium chloride 60 milligram. And those were reacted with the 80 ml of ethyl alcohol in presence of the inert gas such as nitrogen. Later, the synthesized product was irradiated with a visible light at a wavelength of 420 nanometers for 30, 60, and 90 minutes to get the different products of the photo-deposited cadmium sulfide slices BCN as 30, BCN 60, BCN 90. The synthesized product was later characterized by using different instruments like the powdered XRD, X-ray diffractometer, and the Nicoletic 670 FTIR. Then it was further analyzed for the texture using the X-ray XPS analysis and the ICP-MS, and there was a field emission microscope was used for studying its the behavior, as well as optical microscopy, UV visible spectroscopy. So the photocatalytic activity was studied using it was conducted. The reaction for the photocatalytic reduction of CO2 was conducted using 50 milligram of synthesized the photocatalyst and 20 milligram of the bipyridine in 2:1 acetonitrile in presence of water as a solvent. So once it was measured, later on it was studied in the results and discussion as the figure 1 displays the Kersh's peaks of position at 2 theta of 26 degree, that is related to the 002 plane of BCN, and the other peak at 34 degree that belongs to the 100 plane of the same material. Though the peak's position is not shifted, however, you can see that the intensity is shrunk marginally, means exhibiting the basic graphite structure structure of the BCN and fabricated composite of the product CdS/BCN. The prominent peaks of CdS were evidently observed in XRD patterns of the composite CdS, BCN 90 and 60 respectively, which reflects the perfect indexing of hexagonal plane of crystal of CdS. This suggests that the crystal structure of CdS and BCN were well established in composite material. The FTIR study in the figure B, was conducted for chemical examination, and the correctional vibrational bands at 13800 over here and 7800 were studied. Those are concerned with the boron nitrogen and boron nitrogen boron bonds, vibrations respectively. This shows the successful development of the BCN. In the next slide, here it shows the detailed morphological structure study and absorbent feature of the our photocatalyst, that is the cadmium sulfide BCN composite. So from the TEM from the TEM, the figure 2A, actually it elaborates the SEM images of the bare BC, not TM, but it's SEM, bare BCN, and in figure B, the SEM image of our photo-deposited cadmium selenide, cadmium sulfide BCE. So it shows clear images of the small cadmium sulfide nanoparticles, which are photo-deposited and bare BCN. So the figure 2C and 2D, they belongs to the higher resolution ATM images of BCN material. These are the SEM images, and here these are the TM images. Okay, and it shows clearly clear difference of the lattice fringe that defined that belongs to the well-defined structure of the composite material. In the composite with the D spacing of 0.352 nanometers. That belongs to 0.002 crystal plane of hexagonal cadmium sulfide. On the other hand, 0.34 nanometer D spacing pertains to the 100 layer of the BCN. So here in the next slide, you can see the light absorbance study in the figure over here. This one, light absorbance was studied by DRS study. So the figure 3 shows the enhanced optical range of cadmium sulfide BCN composite material at 500 nanometer, which reflects more light absorption than free BCN that was absorbing at 350 to 425 nanometer. This enhanced light absorption reflects the light selectivity effect of cadmium sulfide nanoparticles. And the enhanced optical absorption contributes to take in selectively the large amount of the photon and favorably for boosting the photocatalytic conversion of CO2. On the other hand, the bare BCN has band gap of just 2.64 electron volt, and the conduction band was for the BCN was minus 0.56. Okay, the valence band and conduction band for the cadmium sulfide, on the other hand, are the 1.39 volt and minus 0.101 volts respectively. The valence band and conduction band of the composite material are different from these free materials, which are different from these free materials. So it's the results observed that CDN nanomaterials are operative for maintaining the light, visible light base and electronic properties of the metal-free BCN photocatalyst. Hence, it improves the photoreduction property of the BCN. In the same way, the figure 3 shows, figure 4. Figure shows the bare activity of the BCN material. Figure 4A. Figure 4A shows the bare activity of the moderate BCN, that is at the moderate level of 1.2 micromole per hour to 24 micromole per hour. So for the conversion of assembled catalytic process, the cadmium sulfide was photo deposited. Yes, we have already discussed it, and it showed that little means for the cadmium cadmium sulfide BCN 30 means it showed a little efficiency. However, when we use the cadmium sulfide BCN 60, it showed highest activity, and it was 12.4 micromoles per hour. Means that is and 250 micromoles per hour. From the 12.4 micromoles per hour to 250 micromoles per hour per gram. That is around 10 folds greater as compared to the bare BCN catalyst. So the BCN was, however, when the same means composite material at the BCN 90 was observed when it was studied, it shows again the decrease in the activity, and it was due to the we can say the over photo deposition. So the figure, yes, figure 5, this over here. The figure 5 shows the actually means it shows the CO2 origin, means figure 5 actually shows the origin of the CO that we have obtained. So whether we have to means we confirmed it by using the labeled C13 labeled isotope as a CO2. So the graphs of the GCMS clearly shows the presence of C13 carbon monoxide labeled product instead of the free CO, the C12 normal CO. So from the depicted graph, the peak appearing at 3.27 minutes in GC spectrum, the figure 5A, having the mass charge ratio of 29 in MS spectrum pertains, it directly belongs to the CO2. So from this, it confirms that our composite material is reducing the supplied, or it is reducing the carbon dioxide efficiently. Yes, there are some drawbacks means for this work. Means there is a mismatch between absorption ability of semiconductor and the solar spectrum, and the charge recombination or poor charge carrier separation, because the holes and the radical ions or anions which are generated can recombine and decrease the efficiency of the photocatalyst, as well as the low solubility of CO2 means when we check it in in water can also means decrease the efficiency, or we can say the back reaction of the CO2 once we have decomposed it, once we have reduced it, it can back reaction, give a back reaction, or it can cause a water reduction. So these are the drawbacks that can lead to the decrease in the efficiency of our composite material. Yet the work is in progress to overcome these drawbacks, overcome these complications, and the researchers are working on it, and they have been developing more and more different types of the photocatalysts. So from all this discussion, we can conclude the fabrication of bare BCN semiconductor material in the composite CdSO/BCN photocatalyst by photo deposition method was done, and it proved to be efficient reductive. CO2 broke down into carbon monoxide using visible light in optimum conditions. And the fabricated material was characterized with various photochemical tests, and the optimized material showed 10 times more reduction of CO2, increased efficiency to reduce the CO2 into the carbon monoxide or some other materials. So with the maximum selectivity, stability, durability, because it was repeated 3 times and there was no any reduction in the peak observed. And these are the